on this computer. So yeah, this is going to be a quick little walkthrough, introduction to the Go programming language-ish, but we're basically going to walk through that tool. Jeff and Evan, this will be a really great chance for you guys to see how the whole thing works. And then, is this me? That's really gross and noisy. Evan, can you unmute from me? It's you, buddy. That's totally good. But yeah, so we're going to do a quick introduction to, I think this is about 200 lines of code. And so I think we'll take our time. I've made a point of writing this with tests using a lot of the standard library and sort of like, I don't know, general overview of the Go language. I think it's a really nice, smooth introduction. We don't talk at all about concurrency or Go routines or channels or any of that stuff that is kind of more exciting, I guess, but this is sort of a good fundamentals, I'd say. And so quickly, Evan and Jeff, can you just give me a thumbs up if you've actually had a chance to check the code base that we're talking about, this extract href? Have you both seen it? Ish? Okay, perfect. Yeah, that's actually ideal. So yeah, I guess I'm going to do a quick, I'm going to share my screen and do a really quick buzz through of just like making sure that everybody has the Go language set up and has a couple of really specific editor-specific stuff sort of teed up so that you can follow along, and because I'll show you why in a second. Okay, so let's share our screen. Desktop. I don't know how this is going to work. Okay, can everybody see this window? Give me a thumbs up if yes. Okay, cool. Yeah, so this is, if we hit, I'm going to start right from the top, golang.org, just to make sure that you have everything installed properly. Obviously, you're going to click download Go. Actually going to download it there, but there's this installation instructions is like a link that I think helps with a couple of things. Not only does it give you a link to the Go tools, but I'm pretty sure if you scroll down, oh no, this isn't, where is it? Editor. Okay, somewhere inside on the Go page is a link to setting up your editor with search. Let's do this. No, whatever. Let's do old Google Golang editor setup. Yeah. So depending on your Go environment, you want to have it set up so that you can basically, given any, and I'll show you in my editor now. So to give you the general overview, I apologize for not having prepared a proper link. Where is line text? Okay, cool. All right, so we're going to be looking today at, first I should show you the repo. We're going to go github.com/data-together/archive, or extract href. And so if you want to close this repository, this is the open repository that has all the data. And basically, there's only two files that matters. This vendor folder you can ignore for today. This is just to make sure that installation works really well and clean. But extract is the only file we're going to care about, and extract tests is the test folder, or test files. So now over on my actual editor, we're going to get rid of this file, and we're going to go packages. This is where mine is started. I should probably do this better, but whatever. Extract href is the folder. So this folder is the only one we're going to care about. And I'm going to check out this extract Go. And so this is the actual file we're going to talk about today. It's, how long is it? I'm going to make this big. Let's see it. Oh no, that's not going to work, is it? Oh shoot. Sorry, 1 second. My bad. All right, here's the full thing. It's got a couple of functions. It's got a help text thing, but the first question we should always ask is, what does this program actually do? And for that, we're going to make a new iTerm window. Oh gosh. Wow. Recording and running at the same time is really hard on my machine. 1 second here. Okay. So so by default, our Go destination is always in like your home folder Go. So you're going to do cd ~Go. Oh, also, if you guys have questions, feel free to unmute at any point and just interrupt me. Free form. So Go, your Go folder is where all your Go code lives, tip to tail. So if we do ls on this folder, we'll notice there's only three things: bin, package, and source. Bin is where all of your binaries, your compiled Go binaries go. Go is a compiled language, and so it compiles down to a binary, and those binaries live in bin. If you are on a Unix machine and you have a path, I can do echo path. If that bin folder is on your path, you can automatically do go install, and go install will build the binary, put it in that bin folder, and then you can run stuff directly from it. So in this case, we've actually done that. So to get set up, and the nice thing is, so yeah, we have Go on our machine, so I can tell that I have Go on my machine by running Go, and it gives me just, hey, this is a tool for managing Go source code. Great, that's wonderful. Now the most important, the first point, if you're coming from the world of Node, you have npm, the package manager. If you're coming from Python, you have pip, pip install. We have go get, so we can do go get github.com/data together /extract_href. And so when I type this, what it's going to do is it's actually going to see that github.com is sort of a special reference that's built into the Go tool. And it's actually going to go and get the Git repositories for not only this package, but all of the dependent packages that this thing needs. So by running this, I'm going to go do go get. And so now if we do cd, and it's going to install everything in the source directory. So once again, I'm in the Go folder. I'm going to change directories to Go source. And then I'm going to do ls again. And you can see here, we have a whole bunch of stuff, but most importantly, we have a github.com. So I'm going to cd github.com. And in there, this is going to be big because I have a lot of Go packages installed. But if I do, is this font big enough? Let's make this bigger. I'm going to cd to data together, extract href. And you notice that my terminal is set up to show me the current Git repository, but there's actually, if we do ls, there's actually a Git. The Git repository has been cloned, and I can do git log and actually see the master public branch. And so that's actually how Go manages its packages. There are package managers for Go, but the Go get tool is how most people find and install source code. So if you look at the instructions from the GitHub repo, you actually just run go get, and that gets the thing. And along with go get, what it does is if the code can compile, it'll actually compile and put a compiled copy in bin for you as well. And so now we can finally answer the question of what does this program do? Well, this program actually creates an executable called extract href. And if I do which extract href, you notice that it's calling to my Go folder, which is users b5 go bin extract href. So first thing we're going to do is just use it. So I can actually use this now because my bin folder from my Go folder is on the path. I can do extract href, and that's going to give me the help text. And so what does this thing do? This thing is, for those of us who come from the data rescue world, we often would go to a web page and we would need to grab a very specific set of links to build a collection of URLs. And we know that those links needed to be a special set of properties. They needed to be absolute, meaning they had to refer, be a full URL. They needed to be a deduplicated list. So if a web page referred to that same URL multiple times, it is only included in the list once. And we needed to remove any sort of anchor style tags, href elements, which are links just within the page. So we didn't want any of those because they're just bouncing around the page and we don't need them. And so what I can actually do is I'm going to copy from the example in the thing. So I'm just copy and pasting this. I'm using the extract href with the flag specified here. We have options H, which just prints the help text. O, which is the path of the file to write to. The -s is the string for a jQuery style selector, which is a way of sort of saying, hey, instead of just taking every link on the page, I want to scope that selection to a very specific piece of HTML. Right. So by running this, it's going to go visit the URL I specified with the U flag, and it's going to print one URL per line of deduplicated URLs. And so all of these are valid href elements. And these are sort of all the links that this page that I supplied with the U flag. So Yeah. Everybody following along so far? This makes sense? Okay. Now I can write this to a file because printing out to the standard out is great, but like I'm going to write to desktop urls.txt. And now instead of writing to URLs, in this program, we're going to use some special tricks to know when we're writing to standard out versus when it's not a special trick. We're going to check when we're writing to standard out. And we're going to instead, when we know that we have the standard out free, I'm just going to print the stats from that actual find, which I think is kind of helpful. It's nice to just see, hey, 126 URLs were written. There are 27 duplicates and stuff. And so the program collects these stats, and it's helpful just to sort of show them. Cool. So does that make sense so far? Now we can now that we know what the program does, we can review the code. Cool. Cool. Let's start here. And so everything from here on in is going to happen mainly in this file, but I think we're going to sort of use this as a chance to explain how sort of a Go programmer tends to approach the language. So anytime we're writing an executable, we have a special name for our package called package main. A couple of other things about the layout of this file. Any comments that we want to have, we actually put above the package statement. These are sort of generalized package level comments. And you can actually, yeah, we'll get into the formatting in a second, but anytime you have package main, you need to declare a function called main, which if any of you come from the C programming days, this is the main function. This is how your code actually connects to, once it's compiled, this is the entry point for your code. So whenever we're typing extract href, our first sort of cursor for control flow starts here. And so, but before that is actually executed, we get an init function. That's the only other thing that we get. So we can call init gets called first, which is going to initialize the program. This is our chance to sort of set state. We're using, in this case, we're using the flags package to actually get the flags and set the values that were listed in the help text. And then we're setting them to some variables which are declared at the global scope. We have the main function, which is calling a whole bunch of stuff, and it's going to do some cool tricks. It's just mainly our main, like our super like high level important function is this fetch and write href headers, attributes, whatever. And then we do that check for standards, and attributes is going to give us back some stuff. We'll talk about that in a second. And then we close the file and we output. So the actual main function is relatively skinny. This is sort of the whole thing. And then a few more things that this file contains. We contain a struct definition, which we'll get into. If you come from the C language days, this is the exact same. This is a way of sort of creating a structure, which has a very specific memory footprint that the Go compiler sort of works with. This program also implements an example of an interface satisfaction, which we'll talk about very briefly. We have a quick utility function for getting a results writer. We're going to talk about the writer and reader interfaces very quickly. This is our main function that actually does the cool stuff. And we're going to use one user-generated or user-land package called Go query, which is here. We'll talk about that very briefly. And then we just have like a basic utility like print help text function. So it's kind of the general layout of the whole file. It's not that massive, but I think a lot of the advantage here is its clever use of the standard library. And I want to show you guys just how sort of we work through that. But starting at the beginning, let's just kick it off from the top. So all Go packages have these import statements. This is, and you notice a couple of other special things about Go packages. The first thing you'll notice has to do with why I mentioned the setup of an editor to begin with. Something funny happens when you have all of the Go tools connected to your editor and you actually save a file. So I'm going to do this. I'm just going to hit return a bunch, and then I'm going to hit save. And you notice that sort of changed. And like same thing here. I'm going to indent this a bunch and like just kind of generally mess with code. And this is sort of like how, like normally this would be blasphemy. You would never do this, right? But you notice that every time I save the file, it's reverting it back to a sort of standard form. And this is sort of one of the first things you notice about Go is there is a canonical standard format included with the language. It's called Go Fumpt. Fumpt is a tool that we can actually talk to from the Go command line. Go Fumpt actually takes let's do help. Go help. So this is basically what funct does is every time you save a file, it runs it through this formatter, which determines the canonical formatting for that package. And GoFunct is sort of like our universal way of saying, look, Go programmers have an accepted style. So like in JavaScript, we sort of suffer from a lot of this where we have to self-enforce the style of code that we write. And that style gives us some advantages because the language itself sort of dictates how some of this should work. We get some huge wins. Like you notice I said earlier that above this package main is where we have the package level declaration comments. And that's not just like, that's how I do it or how a lot of Go programmers do it. That is the accepted way to do it. And because of that, we have this other tool, Go Doc. And I can do, I should learn my own program, Go Doc. And so you notice if I type Go Doc from inside of this package, I actually get the output of the package level documentation statement, which is sort of valuable. We can see, you can also see that we have these sort of like statements above. I've sort of kept a fairly consistent strategy for each, what do you call this, function. And so I've new results writer, we have a comment, new results writer writes results, blah, blah, blah. If we're writing a package that isn't main, if I change this to package extracts href, right? So this is now package main means compile and executable. Extract href, package extract href means this is going to be a package that somebody else will import. I'm going to save this. And I'm going to do Go Doc. Oh, wait, yeah. Into, oh yes, sort of really quick. I'm just going to, because we have another, so Go just detected that we have a conflicting name for packages. So I have package extract href here and package main in my test file. So I need to quickly change this and save. If I do Go Doc now, you notice something new shows up because this is a documentation, a package that is going to be imported. It's no longer called main. It knows right away that it should document these individual functions that are exported. So that brings us to the other really funny thing about Go, which sounds strange at first, but is very, very helpful. Anytime you see a phrase that starts with a capital letter, meaning like new results writer, capital N, this means exported. If we want it to be a private method that isn't exported from the package, we change this to a small n and save. So you notice here, we had new results writer is I'm pointing to the screen like you guys can see that. We have this new results writer here. If we do Go Doc again, now that I've saved with that lowercase new results writer, you notice it's gone because it's no longer a public function. And so this is this becomes this is sort of the idiom all over the place, including inside of struct definitions. If you see capital E elements, that means it's an exported property of that struct. If it's small e, that means it's a private property. It means you can't access outside of this package. Stats.elements would not be available. But and the same with the struct itself. If this is a lowercase, it's stats would not be exported. And so if we do this again, and we see that we had stats listed as a struct that's available, stats is no longer available, right? And so this is I found it to be a great convention. It's very helpful for like just sort of keeping track of, I can look at any function at any given point and know whether it's an exported function or not. I can look at any structure and know whether it's exported. Private fields are kept private. It's kind of a nice and easy idiom to keep in mind as you're working. The other thing you'll notice about Go that I can't believe I haven't covered until now is Go is strongly typed, meaning that every variable always has an assigned type to it. It is illegal in Go to, so in this case, stats is a structure that has a property elements of integer type, s.elements. This would break everything, and this will fail to compile, right? Because I'm assigning a string to an integer. The kind of gotcha from the strong, so there's a whole lesson about strong typing and why not that. It's worth, for now, it's worth it to just say that Go is compiled, and that's the deal. But there is one funny sort of thing that you'll see all over Go code that kind of is related to strong typing, but is meant to make the code more readable. And that's this phrase right here. I don't know if you can see this okay, but this colon equals, you see it all over the place. W error colon equals, right? What colon equals means is infer the type of the variable from the right side of the colon equals statement. So if we look at our function new results writer, the Go, we can return multiple things. We don't have to return a single arguments. Just like Python, we can say, hey, I want to return an IO writer and an error. And so those two types are the return values of this function. And the accepted arguments is a path. So up here, when we type colon equals new results writer, W is by default an IO.writer, and error is of error type automatically. Does that make sense?
Yeah. What happens if, let's say, you just assigned one variable to that output? Mm-hmm. Is it the tuple, or does it error?
It is. So you will actually. That's a great question. So as soon as you do this, you'll notice I'll get a compiler error here. It'll try to recompile this, and it should give me an error. Actually, I think I need to first. First, let's go back to main. Just give me 1 sec. So Go is extremely explicit. And this actually drove me nuts when I came to the language at first. This broke, and I was so upset. I didn't understand how it worked. If you always have to take the right number of values. So in this case, if you wanted to ignore this error, you actually have to type comma underscore, which is a way of signaling to other programmers, I'm explicitly ignoring a value. And so that's always required. If you assign a variable, if say we were to, we'll get another special kind of error if there are no new variables on the left side of colon equals, it will also say there's nothing to infer here, and so it's illegal. And so in this case, is error assigned earlier? So like if I were to declare var W is of type IO.writer and error of type error. And in Go, we could do this sort of braced error style or braced variable declaration. And so I've declared those two things, and I'm going to say error. And you notice I'm getting a dot in my editor, and it's saying no new. I don't know if you can see this. It's very tiny in the bottom left of my editor. It's saying no new variables on the left side, and so that's a compiler error. So if I save this and do Go build, it'll give me a compiler error saying, hey, on line 65 of extract, there are no new variables on the left side of your colon equals. And so that's because we declared them already, and there's nothing here, right? And so same thing, just to show you an example of what you're asking about, Jeff. If I do this, multiple value new results in single value context, right? So you require to sort of answer every value. You can, however, it is totally legal to do nothing, which is hilarious, right? But it's, you could do that because sometimes you want to call functions and not worry about their outputs, just sort of deal with their effects. So that's how that works. Let's delete this. Let's get back to the right spot. Cool.
One quick follow-up.
Yeah.
Is underscore an accessible variable, or is it just go into the...
No, yeah, the underscore is blank assignment, meaning it's not an accessible value. So you can't ever read from the value of underscore. Underscore is intentionally, so the whole sort of theory behind Go is to make somewhat verbose but incredibly readable code. And so the definition of underscore is, hey, other programmers, I'm ignoring this. And so whenever you it makes for really nice code reviews, because now when I see this and someone has submitted this as a pull request, I'm like, oh, you didn't handle this error. And so we don't accept this because we need to handle all errors, right? And so, yeah, does that make sense?
Yep.
Cool.
Thanks.
No worries. Yeah, and so this kind of, that gets us to like a pretty good starting point. So now we've covered strong types very briefly. We've covered multiple returns and colon equals. We've covered our main and init, our package definition stuff. Now I think the next best thing to sort of get onto is we can actually start to talk about the standard library and the actual definition of this program itself. So the first thing you'll notice is it can be kind of frustrating sometimes to deal with our command line arguments when you're writing a command line client, right? Actually getting the getting values out of a flag. And it's because, and this is even more so in situations like Go, which is a strongly typed language, because you need, like, you can't just accept anything. You have to sort of parse that out of a string, turn it into a Boolean value. It's kind of a pain to do type conversion. So you want sort of nice stuff for that. But anyways, yeah, so we're using the flag package. And this is why I sort of covered very quickly setting up your editor to sort of see, to be able to see what a package does, because a lot of your time in Goland, when you're first getting used to that, actually even to this day, I use this all the time. I have my editor configured so that I can, at any given point, okay, I can break my editor apparently. No, that's not what I intended to do. Okay, let's try that again. I can type this special command, which gives me access to, oh gosh, this is gonna be really slow. Okay, cool. Which lets me sort of look at the flag package at any given point. And so I click enter on flag, and then I'm gonna look at the flag. And this is the actual flag package itself, right? And this explains how to use it. You know, this was written in 2009, implements command line flag parsing. This is how it works. This is what it does. And this is like sort of everything that this package uses and does. And so while I'm working, like while I was writing this code, I don't remember, you know, flag.bool there. I don't know. There's too much to know. I don't use the flag package a ton, and so I'm relying pretty heavily on code completion because we do have a pretty heavy standard library here. But also, I can sort of, at any given point, my editor allows me to type alt.g, and I can jump directly to the definition of that function. And I think this is really important for Go because you end up reading a lot of the Go source to understand how the language itself works. And the standard library is a really valuable sort of set of tools that you should be drawing on as much as possible. And so in this example, boolvar defines them. And so like I actually will, like in constructing this package, this isn't like some made up example. I came in and read this comment, like, okay, that's exactly what I want. I need to feed this guy a pointer. Oh yeah, Go has pointers. I can't believe we didn't cover that. So like, but there's no pointer arithmetic. That's worth noting. So I don't know if you come from the C world where you can actually like, do like pointer A times pointer B to get different places in memory. You can't do any of that stuff in Go because it's a garbage collected language. But this N symbol, what that means is take a pointer to. So you'll see this a lot in allocation. In our fetch and write href hatchers, I'm going to give you, like, for a quick preview, we allocate a stats object right here. So this is what this sort of statement is saying is give us a new stats object, which would look like this. And then because we want a pointer to its stats object, we add this N symbol in front of it. And now what that means is we have a pointer to stats. So the value of stats in this case is pointer to stats. And again, we're using that colon equals because this is this is sort of like the equivalent of like malloc, allocate this piece of memory. Cool, we got it. Let's take a variable that's a pointer to that in one sort of succinct line. Yeah, and so in this case, we're taking variables we're declaring these flags. This is actually how the command line help text gets printed out. And so we're using the flag package to just deal with the minutia of setting up flags. And so we actually end up leveraging that last thing. That flag print defaults is how we actually get the help text that shows the flag. So I don't actually have to maintain that text. It's just there, right? And so I didn't realize that flags print defaults existed in the package, and I was like, oh, that's sweet. We can at least cut that corner. And so it's nice. You do a lot of reading, so I'll quite routinely, having code completion is really nice because you sort of get in here. And it's not uncommon for me to type flag dot and then just kind of like go exploring. Like, oh, what does this do? What does this do? What does this do? It's really kind of a standard way of investigating language. Anyways, cool. That's what the flag package does, allocates those flags. First thing we have to do in main is called flag parse one time. what that does is that actually like parses the flag arguments. It does all of the work of assigning the values to these variables. And so once we've called flag parse, all of these are now populated with whatever the user set them to. And if not, they have their default values, which comes from there. That's also worth knowing. Go has sensible default values for everything. Now, by sensible default values, I mean, you notice in the stats object I mentioned earlier, stats has elements specified, which is the length of the number of elements that the Go query package spits out. We'll get to that in a sec. But you notice that stats as a structure has other things. And so in a lot of other languages, when you allocate a new thing and you don't specify what the with href value is, that would be null. And that's not the case in Go. In Go, when you make a new stats object, the implied value of this stuff with href is 0. The default value for an integer is 0. The default value for string is empty string. And so that kind of affects the entire language because for two reasons. One, the only time you compare to null is when you're dealing with either a pointer or an interface, which is a kind of pointer. We'll talk about in a second. Every other time, you have to compare to its default value to check for falsiness, right? So you're used to sort of saying like, hey, blah, 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 blah. Are you null? Cool, you're not null. All right, then I'm gonna do stuff. Wow, that was a really helpful statement. But hopefully you understand what I mean. There's, instead of comparing to null, we compare to default values all the time. So if I wanted to find out if the value str is foo, and if I wanted to see if str equals, this is the equivalent of like checking for falsiness in Go, because all values are initialized with their default values, which you can look up in the Go spec. But the default values of float is 0.0 forever. The default value of true of a Boolean is false. The default value of any kind of pointer is just like you can declare structs that have pointers. Their default value is null. You notice the other kind of funny thing about the language is there's no brackets around here, right? They just took them out of the language. You'll also notice that there's very little use of semicolons. There are times where you need it. The only real time that is sort of like practically shows up a lot is your classic for loop with a iterator allocated inline. So I is less than 5, I plus plus. But Go has a very clean definition of when you need a semicolon. It's when you need to delineate two instructions. Otherwise, it is, so every executable, I should look this up because somebody in the Go community is going to scream at me for saying this wrong. But long story short is that you only need it if you're evaluating multiple expressions per line. You will see that sometimes in, let's see if we have an example of that. So in this case, we can actually restructure this to say if, here, and then I can actually add a semicolon and make this something of a one-liner. And what that does is, this is an if statement, we're evaluating an expression, semicolon, and then we're gonna check the value of the errors. It's also worth noting that in Go, the scopes are much more accurate than what you think. Inside of, or it's kind of closer to what you would assume. So in this context, this would break the program because this if statement actually creates a closure, meaning I've declared response and error inside of the evaluation of this if statement. So here response is the result of this. So here response is declared, but out here response is nothing. It's not a defined value. And same would go if I were to type another if. And it's nice because what it means is every time you see curly braces, you're in a new closure, right? So it's every time you see, if you declare a variable a in here, it's colon equals 0. A does not exist out here. A does not exist here. Is that true? No, maybe. I don't know. I apologize for not being master of the universe in this one. It'd be interesting to find out if A is defined here. Can't remember. Sorry. Cool. So let's undo this all the way back. Okay, cool. That's where we were. Yes, so strongly typed, multiple return values. So the question that most people ask at this point is like, okay, but what about like classes? And what about like object orientation? How does that look? How does that feel in Go? In Go, we don't have classes per se. We have something called embedded structures. So I can declare a type super stats. Wow, my thing is so slow because I'm recording. But anyways, and I can do stats, just blank. And what this says is embed a stats object into superstats, and then I can do like new field. Oops. And so in this case, all of stats' properties are now first order part of superstats. So I can actually now type superstats.elements. Does that make sense? Okay, cool. This is struct embedding. So if stats has methods defined on it, let's look at how that works. This is how you define a method on a struct. This is the receiver of the method. And you'll notice that this has a star, which means a pointer to stats has this method, but a stats object itself does not have this method, if that makes sense. So that's why, because that method has a string as its receiver, that's the reason later on, we'll get into it. Actually, we won't get there quite yet. But suffice to say, this is how you refer to yourself and how you define methods on structs in Go. So s.stats in here, I can actually leave s unreferenced if I don't actually need any of the values. That's perfectly legal. But s.string, you notice it has a method string now because it's a pointer, this would be a form of recursion, and this would break the program because I'm calling string for infinitely. But we can declare, we can declare methods on structs. We can embed structs into other structs. Most people don't do a lot of embedding. Someone have a question?
Yeah, what is small s in this case?
Small s is the actual stats pointer, so I can do stats.elements. Does that make sense?
Oh, it's a variable that's holding the pointer.
Exactly, and it's referred to in this context as the receiver. It's the receiver of the method, right? And so anything on the left of the method definition, you're only allowed to have one receiver. So there's one thing here. If this is unspecified, this is just a general function string. This is a function that is only on the stats method. So I have to do, or the stats struct.
The second element is a type for small s.
Yes.
Is that where small s is getting defined too, and that function stats?
Exactly. So I can actually name this, foo, and that's totally legal. And so you notice there's no concept of this in Go at all, or self. That doesn't exist. You always have to define the name of the receiver, and then that's what you call it from then on in.
What's the scope of s? Just that definition?
Yes, exactly. And so this is a method. It's defined. To get to this, you actually have to allocate a stats struct pointer specifically, right? Does that make sense? Like in here, where is it? I've created a stats pointer. So I can in here I can type stats.string, and that gives me a string value. But interestingly enough, if stats, this variable was a value instead of a pointer to a value, to a stats.string, oh, I guess it exists. It shouldn't exist. But I guess it's kind of there. Anyways, yeah, that shouldn't be there. I guess I just need to save the file. I don't know, whatever. It shouldn't be. That would be a bad idea to use it that way. Or maybe I'm off. But yeah, does that make sense? Any follow-ups?
Yeah, I think so.
It's a bit to take in. Methods on structs are kind of the way that we make composable, transportable units. You'll see that kind of code a lot. But most importantly, how do we do stuff like classes? How do we do like sort of generalized reference to stuff, passing around things, right? This is where the concept of interfaces comes along. And so an interface, to show the concept and just to give you some examples. This io.writer is an interface we've been referring to the entire time. Where else is an interface in this package? I think that's the only one. Oh, new document from reader is defined in the Go query package. Reader is a type of interface. If we check out this documentation, this is perfect. This actually, the argument that this accepts is of type io.reader, right? And I've passed in the response body from a HTTP request. So if we look at response.body, you notice that it is of type read closer, which is also an interface. It only has two methods, read and close. And that's because it's satisfaction of an interface. So let's look at what that means. Because the definition, it seems like we need to know the definition of io.reader. So I can actually surf to new document. So this is in the Go query package, new document from reader. So this is importing io.reader, and then I'm going to surf to that. And this is the definition of the reader interface. So this is the other use of the phrase type, type reader interface. This is not a struct. This is not the definition of a piece of memory. This is not the definition of a class. This is the definition of a collection of behaviors. And behaviors are always functions. So the only thing you can put in an interface is a function. So the definition of a reader is a function, anything in the world that has a method called read, that has a function called read, that accepts a slice of bytes and returns the amount of bytes read and an error. Everybody follow that, kind of? So I could break the reader interface right here by saying foo error, and now anything that's going to call itself a reader needs to also have this method foo. And the compiler would say, hey, actually should we be saving changes to standard library? This is horrible, but whatever. Let's give it a shot. This should blow everything up. Oh, what? That's unimpressive. Oh, wait. I don't know, whatever. Oh, yeah, it pulls, sorry, my editor pulls the actual source code from a different place than the actual compiled stuff. But we could take away, we could feed this. Yeah, so we'll feed it the response instead of the response body. And it's going to give us this, oh no, yes, go build. And so it's going to give us this error. Cannot use response type pointer to HTTP response as type io.reader. The response does not implement io.reader. You're missing the read method, right? And so this is how Go programs get decoupled, is instead of accepting values or specific things, whenever possible, instead you just think, okay, what are the parts of this method that I'm actually using? And I'm only going to ask for an interface that declares those parts. And so we like these really small interfaces, and we like to just pass around composable units in ways that makes that sort of straightforward. So in this case, response body does satisfy you'll notice response body is actually a reader closer. It has both the read and the close method. But new document from reader doesn't care about the close method. It's never going to call the close method, so it doesn't ask for it. Does that make sense? Yeah, and so that's how we actually, and so like, there's some really exciting interfaces that we can refer to, like for those of us who have been surviving the conversations about converting to the data store interface from the Protocol Labs team. Where's that definition? I'll pull that out at some point. Actually, yeah, let's just do it right now. Data store. So this is the Go data. You'll often see these kinds of packages that just declare interfaces, and all this is hey, this is how all of us are going to communicate about this kind of stuff. And so a data store is a key value interface that lets us put stuff into it and get stuff out of it according to this key property that we declare in this package. So when you want to implement the data store interface, all you do is, you don't have to import this package. You end up having to because you need this key property. But you wouldn't have to import this package at all if not for the key property. You can just write these methods onto your function or onto your struct, put get, has, and delete. And as long as you satisfy them, you satisfy the interface, and that's called implicit satisfaction. And now your thing can work with, I can pass that to stuff that take the data store interface. And so that's why we converted a lot of our code to say, hey, we don't want to take Postgres drivers. We want to take just data stores, right? Because that means our code is much more robust. We can plug in Redis data stores instead of Postgres. We can do all kinds of cool stuff. And so what is, and you'll notice that something funny about this program that is because of interface satisfaction. We declare a method called string on stats, but we don't ever actually call it anywhere, which is kind of weird. But you'll notice in the main function, we have this println stats. And so what this is doing is this is the conditional I told you about at the beginning, saying, hey, when you are writing, if we're not writing to standard error, we should use it. We should print the stats to standard error. The nice thing about the funct package is the funct package knows to look for something called a stringer. And a stringer is an interface. I wonder what package declares stringer. Ooh. I think it's in funct. Okay, let's find out. Geez, it's been a minute. Format. I don't know. Where's stringer? Oh shit. I wasn't supposed to swear. Sorry, 13-year-olds that are listening to this. Anyways, funct, you just have to take my word on it. Funct takes, it's somewhere, and I use it so often, but don't declare it. But basically, by creating this method on struct, that on our stats struct that is called string, when we send this thing to funct, shoot, sorry, I should be scrolled to the right place here. When we send this thing to funct println, which means print this thing to the console, and we hand it the stats, it checks to say, hey, do you satisfy the stringer interface? And if so, I'm going to call that method for you. And so let's take a quick second to detour. And so I'm going to save, and I'm going to run this once with as it currently exists. And it prints like that, right? Now let's see what happens when we delete the string method. We're going to comment this out and save that. And I'm going to do go install. Thank you. And I'm going to do this. And you notice that it just prints the value of string, which is the actual solid structure definition, right? So this is technically number of elements. That's technically what the second with href and duplicates and valid URL, right? And so it's this implicit satisfaction that becomes the really exciting part of Go. You can sort of later on, it makes refactoring code as your code base grows really useful because you end up noticing patterns in your own work. You're like, oh, I've declared this same method across these three things. I can just write an interface that accepts that method. And instead of taking any of those concrete types, I can now just accept that interface. And so it means that refactoring code is much more straightforward. And if I need to, I can get my head around a program and how it works. I can just start reading the interfaces. And now that's sort of the definition of the seams between packages, the seams between functions. And it sort of makes a lot of this much nicer reading. And so in this example, fetch and write. So this is a great example of how we're using the interfaces to our advantage. I'm saying fetch and write href attributes. This is this is kind of the whole point of the program, right? Go get the stuff, grab the href attributes, and write it. But I want to be able to write, my package specifies that I can write either to a file or to standard error, right? And I don't want to use that. I don't want to change that, and we're strongly typed. So if you look at our definition of fetch and write href attributes, we just accept an IO writer, right? And what that means is we don't care. As long as you have a write method down here in the actual loop. So, okay, let's walk through this really quickly. Basically what we do is we find the selector that we've been provided, which gets passed into us. Normally that's a command line flag. But then we create a stats object. Then we iterate through every node that we find. We check to see if it exists. If it does exist, then we know that this element has an href attribute. And then if it's, and then this root.parse is a great example of Up here, we use the net URL package to actually generate the root URL as a URL structure. And then when we call parse on it, that has the effect of absolutizing the URL itself. So calling this URL and having it parse an href means that it will check for any relative link and it will just automatically resolve it to that page, which is exactly the way the browsers work, right? And then if we have a fragment, remove it. And then this is rendering the string. So yes, this gives us the absolute URL. This absolute.string, again, we're abusing the stringer package. We're just saying, hey, or the stringer interface, we're saying, hey, you have a string value, and this gives us the actual URL as a string instead of as an object, or as a struct, sorry. And then in this, we just check, hey, is this string the same as the root URL? If it is, it's a reference to itself. That's useless. And then we have this map of added strings. Basically, here's everything we've already added to the list, and it's just map of URL name and then Boolean, which is just true. And so if the map of this, again, the default of something not being present is false. And so we say false. So the first thing we do is, okay, we know that we need to add this to the list. We set that on the map to true. We increment our stats to say it's a valid URL. And then we use this writer write method. And this GAC is convert this to a writer accepts a slice of bytes. It doesn't accept a string. And so this is convert the output of funct sprintf, which is print just, instead of printing to the console, just print it out to an argument. And this is just saying add a new line, which gives us our text sort of thing. It gives us one URL per line. And then we write that to whatever our writer was. So if the writer is a file, it'll just write it to the file. If the writer is standard error, it'll write it to standard error. And so otherwise, and then in this case, if this is wrong, we know that that URL is duplicate. So we add increment duplicates. And then we just give that the stats object, because that's what our function signature asks for, and any error. So the other pattern that, just to sort of round this out, you'll see a lot of this pattern in Go. Hey, is error nil? If it is, let's bail. Hey, is error nil? Is error not nil? Sorry, we want error to be nil. And so this is just the early return kind of principle. But you see this typed a lot, this like, and that most people who come new to the language sort of feel like that is like kind of redundant and irritating. But it's nice to see from the reader's perspective of the software that like, hey, this is me handling an error. Yeah, I got you. I handled this error. I handled this error. I handled this error. You know, it's good. And so that's kind of the general reason for doing that. But yeah, does that, so we write to a writer, we accept a writer, that makes this function nice and robust. This means that I wrote this with the intent of sort of pulling this out of the command line context, and we could later use this somewhere else, right? We could put this in our task management server and have this thing just execute somewhere else. Finally, in another sort of session, I was hoping to go over tests. Go has a standard included method of writing and writing tests. You can read more about it, or you can just have a look at this test set yourself. Suffice it to say, we can always just run go test, and that will check. And then we can do go, my favorite sort of demo for the end of Go, because the tooling is really good. We can do go test cover profile equals coverage dot out. And what this is going to do is it's going to run the cover profile. It's going to check, okay, I have 50% coverage, and then I can go tool cover HTML equals coverage dot out. And what this command does is this opens a browser that checks my source code for which things are being actually hit by my tests. Green is the test is checking it. Red is the test is not checking it. And so like, this is a nice example of like standard library sort of showing, and like, you know, I didn't handle this error, so I should probably get in there. I should make sure that my tests sort of penetrate deep enough to actually get that, to check that value and make sure that that's a valid thing. But you notice that like some of the stuff that's costing us on our coverage is like this print lin of the help text. It's not the most vital thing in the world. I'm not going to lose sleep over not testing that, which we should. I mean, we should, you know, we're good programmers. We should get test coverage up in the 80s, but maybe even 90s. I don't know, depending on how pedantic you like to be. It's worth noting that you can't test the main function. But that's why I've sort of like pulled it out as much as possible. I don't know if that's true anymore. I think you can actually, there's ways, but whatever. Anyways, whew, that's a tour. How's everybody feeling? Good, great. Any questions? I'm going to assume no. Nope.
I don't know if you have time, but can you go over how the data structures are declared?
Yeah, like struct definitions.
Or like lists and
Oh, yeah. Yep.
structures there?
Absolutely. So we have some examples of that in our extract file. So yeah, I didn't even introduce the concept of slices. That's awful. Go does have the concept of static arrays, which is like, but nobody uses them. I mean, you use them, but only in very specific places. But you declare slices and maps with this special function called make. So I can do make slice of stats. This would be a slice of stat pointers. And then you have to declare how long you want that slice to be. And so a slice, when you hear the word slice in Go, just think array. Array, slice, same thing. The reason they have a special name is because SL is you can do special stuff. Like you can do SL. So let's pretend this is an array of stats objects that's 10. And like you can actually index. This is slicing into this slice from index 0 to index 9, and that will return a newly allocated array.
Is Go a closed index? Like, is the last element 9 or is the last element 8?
Last element will be 9.
Okay, cool.
Yeah. Yes. Yeah. So, and then conversely, we can do 3 to the end, or we can do 3 to 6. 3 to 5. Concatenation of arrays is there is no concat function. There is an append, which is append SL, and then you can add a new value, which must be a stats pointer. So that's, and then, oh, what did I do? So this would be SL equals. So that's the result of adding a new thing onto the end. You'll often see that sort of like this equals append itself. You also have, and then allocation of maps is the exact same. Maps are specified with the type map, the word map in front of what looks like a slice. So map string. But you could have there are certain types that are keyable and there's certain types that aren't. You can't, for instance, use a stats object as the indice. But you can do string, you can do ints, you can do a lot of the primitives. You can't do bools, that wouldn't make a lot of sense. But map and string to stats pointer. And as with arrays, you can allocate this with make. But this doesn't make as much sense for maps, right? Because like, why am I doing a length? And so the other form to allocate stuff is using the standard allocation method, which you saw me sort of erroneously type this already. Map string to stats. This is so hard typing on this lag. Cool, and so like M is this. And this is basically saying allocate empty, but if I wanted to put things in this initialized struct, I could do stuff, and then like I'd have to declare a stats pointer here. Does that make sense? And then indexing into this is literally the same as you'd expect. If this would give you back that stats pointer. What else? Same thing with slices. You can still do like SL. 4, that's element 3 in the array. Yeah, does that help, Jeff? Any follow-ups on that? Yeah, there's lots of this. It's interesting because we also use make for channels, chan int, which we haven't talked about today. But channels are our concurrency primitive for communication between Go routines. We haven't talked about Go routines, but that's the keyword Go func blah. That means do this in parallel. That's the like actually exciting stuff, but we'll cover that in another day. But yeah, that's kind of the general outline of it. Any other questions? No? Cool. I think that means we're finishing just on time, 2 minutes late, but who's ready to go to a data together meeting? Yeah, these guys. Okay, cool. All right, guys. Thank you so much for listening in on this. Hopefully those who watch the screen share will find this valuable. Okay, and then I'm going to stop sharing. And hopefully that works. Stop share, come on. There we go. Cool. All right, so see you guys in the other call. Well, yeah, I'll see Jeff in the